Hi, this is a presentation of our WCV paper on learning to recognize occluded and small objects with partial inputs. We tackle the task of multi-label image recognition where the goal is to detect objects and attributes in an image. This has applications in tagging social media images, autonomous vehicles, and scene understanding in general. The task is challenging due to large variations in the size and spatial location of objects. This gets even harder when the objects are occluded and small. Recent methods for this task are complex in both model and data. They do not explicitly address the problem of small objects and occlusions. In terms of model, the methods use multiple stages of training. They combine multiple learnable networks into a single framework and rely on large language models. In terms of data, they tend to use high input resolution, complex data augmentation, and additional data during training. To address these issues, we propose Masked Supervised Learning as a new deep visual learning paradigm for multi-label image recognition. This has three main components, which are the image recognition branch, the masked supervision branch, and label consistency. Given an image, we mask the image to simulate occlusions, which can be also thought of images with partial inputs. The goal of these two branches is to align the predictions between the original branch and the masked branch, and thereby learning context. We can use any multi-label image recognition model using this framework in a single stage training paradigm using the loss function defined here. The masked branch aims to learn context-based representations so that it uses nearby non-masked regions around the objects to make predictions for partly visible or masked objects. Label consistency, on the other hand, models label co-occurrence by learning a distribution of association across the different classes. We can also think of it as it uses context to infer presence of a class from the labels. We test our method against state-of-the-art multi-label image recognition methods on multiple popular benchmark datasets. We find that MSL is accurate and computationally efficient compared to recent methods. MSL is effective at recognizing small and occluded objects compared to baselines. This is because during training of MSL, it is able to learn contextualized representations. MSL is robust to heavily masked inputs at test time, which is also a good indicator that it can work well in cases of occlusions. MSL is able to recognize heavily masked objects and also works in cases where the object is almost completely masked. This shows that MSL uses context to infer presence of heavily masked classes. We also compared MSL against a self-supervised learning method, masked autoencoders. In this case, we also found that masked supervised learning outperforms this method. It is also noteworthy to mention that masked autoencoders is a two-stage learning framework, whereas MSL is a single-stage learning framework. MSL also enjoys heavy masking. It is also generic and applicable to any model architecture, making it model-agnostic. Another property of MSL is that it predicts non-masked objects better in comparison to baselines. Overall, MSL is a simple yet effective single-stage model-agnostic learning paradigm that uses masking. It leverages context on both image and label level to infer presence of multiple objects, even in cases where the objects are small and occluded. In comparison to recent methods, MSL does not require multi-stage training, combination of multiple networks, reliance on large language models, high input resolution, complex data augmentation strategies, and additional data for pre-training. For future work, we aim to apply MSL to other computer vision tasks, such as object detection or 3D human pose estimation.